Okay, Year 10, this is Mr. Tickner, and this is a recording of the latest paper you sat. There are timestamps below to each question for you to have a look at the ones that, if there are specific ones you want to have a bit more information on and how they're solved. So, starting with question one. Question one is largely about recall. I'm just going to go full page. So we have a 4-mark question on linking each sort of EM wave to its use. This is something that you should just be recalling because there are always these marks. If you get all of them correct, you get 4. Then for each every mistake, you go down by 1. The one which is not specifically in the spec is UV is detecting forged banknotes, but by process of elimination, you can work out that it's the only one that's there, and it's also in it's something we need to talk about. State hazards of excessive exposure to infrared. The term is skin burns or burns on the skin. Just make sure you don't confuse that with a sunburn, because a sunburn is a reference to ultraviolet radiation. And then any precaution that would reduce a person's risk of exposure to UV waves. Anything sensible, really. You want to either minimize the time of exposure or have something that's going to block it. And that can be anything: sun cream, wearing a t-shirt, getting in the shade, not spending all day out in the sun. Anything sort of sensible, the sensible stuff you do in the summer to avoid getting a sunburn. Okay, and that is question 1. Question 2, again, more sort of recall. So we've got a picture of a wave, a water wave, traveling on the surface of water. Which arrow represents the amplitude? And the amplitude is S, from the midpoint to the peak. Which arrow is the wavelength? It's Q. We've got one peak to be distance. It's one whole wavelength. What type of wave is this water wave? It's a transverse wave, because water waves are transverse waves. You can work it out from the diagram because this is height and this is where we're going, but we've got a transverse wave here. Okay, and then we have a time period of the wave is 2.7 seconds. Calculate the frequency of the wave. The equation you need to use is one that's given to you. Frequency is 1 divided by time period. So you get 1 mark for putting the numbers in, 1 over 2.7. The other mark is therefore for working that out. Comes out as 0.37, or anything that would round to 0.37, you get the mark for. As with all calculations, if all we see is 0.37, you would get both the marks. Great. Question 3. We've got a picture of a toaster. It's an electrical device used for toasting bread. It contains thin metal wires. These wires get hot when there's a current in them. The wires transfer energy to the bread by heating and by radiation. Give a reason why the wires in the toaster are connected in parallel. So the most obvious answer, the one I thought of instantly, is that it's this quite classic idea. The advantage of putting anything in parallel is that if one of the wires breaks, the others stay on. It's the big advantage of a parallel circuit. And this does get the mark. However, the first answer they've got in the spec is that each wire will get higher voltage, or each wire, if you put them in parallel, you can draw a bigger current. That's the wrong thing there. So you can say you can talk about drawing a larger current than if you put the 48 wires in series. You'd be making the resistance quite high. So in the first answer they got in the mark scheme is this reference to this lower one, but the top one is a perfectly valid point, and that was my first thought anyway. So we then have a formula. So to state the formula linking power, current, and voltage. Stating the formula, get a mark. Power equals current times voltage. In any order, in words or symbols, it's all perfectly fine. And then we've got the power rating is 2.8 kilowatts. Calculate the total current in the toaster. So the first thing we need to recognize is that 2.8 kilowatts is 2,800 watts. It's going to be important. So we get 1 mark for substituting. 2,800 is equal to the current times 230. That gets you 1 mark. We then have to rearrange it. So we have to divide through by 230. So your second mark is for showing you've rearranged it, or put it in the form of what current equals. And then your third mark is for working it out, and it's 12.17. If you, however, just write 12, you'll get the marks. You don't need to write 12. You don't need to write it to 12.17. 12 is fine. So there we go. The toaster contains 48 thin metal wires. Calculate the current in each of the thin metal wires. Now, what we've actually got going on here, if we draw our little circuit, we've got our 230 volt supply, and we've gone into our toaster, and what's actually happening is we're splitting this current into the 48 wires. I'm not going to draw 48. Okay, so we've just got 48 wires. And so what we've got is our current that's going in is 12.17 amps. That's what's going in. And we're now going to split it up. We split it into, so the current is splitting up at that junction into 48 different bits. And if you do 12.17, you divide it by 48, you get 0.253, I think is the real answer. But if you just use 12, you'll still get the same answer. You get a quarter of an amp. So each individual wire is just going to take 0.25 amps. And they get to the other end, and then they rejoin again, and we go back around to go back. But it's a 1 mark question, so that's it. Right, question 4. Well, there's a few things that start getting a bit more wordy. Okay, so we've got a diagram. So we've got a wave and coming in. We've got some wave fronts, and we're asked to draw the normal at the point where the direction of the waves meets the side of the boat. So it's a 1 mark for drawing this red line. You don't need to label it as normal because it's obvious what it is. Doesn't need to be a dashed line, it can be a solid line. You should use a ruler. I do not have access to a ruler on this software at the moment, so this was quite hard to draw. I do recommend using a ruler. So we have that. That's our first mark. Measure the angle of incidence of the water wave. So we need to measure the angle from here to the normal. And the answer they think it is 66 degrees, but you're allowed there's a bit of leeway because you might mismeasure it on your protractor very slightly, or you might misdraw the normal very slightly, and that can compound it. So any measurement between 64 and 68 is allowed. And the third bit is complete the diagram to show the wavefronts after they reflect off the boat. So in order to do that, what we know is our directional wave is going to follow an angle of reflection. So this reflected ray here, if I had measured this as 66 degrees, then this angle is also 66 degrees. Now what's important is that this measurement here is by eye. You don't need to draw it out explicitly. You can, but it just needs to look right. Okay, so this reflection looks right. I haven't measured this with a protractor, but by eye it looks like it's correct. So I've got a correct reflection. And then what I want is I want the wave fronts. They are going to be perpendicular to this direction, direction of travel, and they're going to still be equally spaced, and they're going to be in there. So we've basically got 1 mark for the wave fronts, and the way they mark it is in this region up here. So up and right. The second mark is that they are equally spaced and parallel. Okay, and the third mark is that we've got essentially we've got a correct reflection by eye. So they're in the right place. They're up here. They're not down here, or they're not going. So they're in the right place and they're at the correct reflection. So if we drew some wave fronts, that were say like this, we drew that, then we would actually get 2 marks because they're in the right zone. They're equally spaced and parallel, but the thing that's wrong is that this is clearly an incorrect angle of reflection. That immediately would look wrong. So there we are. So then we get a bit of some wordy stuff. So let's deal with this. The boat starts to move, creating its own waves. This surface waves, water waves, and transverse. Describe the difference between transverse waves and longitudinal waves. And this is, again, a bit more, this is really kind of recall. It's like, what's the difference? We want to say that the key thing is that transverse, the vibrations or oscillations are to the direction of energy transfer or wave direction, or whatever, whereas longitudinal is the same sentence, but instead of perpendicular, we'd write that you know, we write vibrations are parallel, okay, to the direction of energy transfer. Those are the two sentences, and that gets you 2 marks on that. We then have the Doppler effect question, which if you say nothing in this, it's credit worthy, but you just mention the Doppler effect. If you just say Doppler, you get 1 mark here. Okay, but it's a self-contained mark. If nothing else you say is credit worthy, you can get 1 mark for getting Doppler effect. Explain why the frequency of the water waves measured by the observer is larger than the frequency of the water waves created by the boat. Okay, so what we need to say here is that if we look at what's going on here, the observer, the wavefronts have been compressed. Okay. Okay, thanks. Reduced. Okay, a bit of an interruption. The second thing we can say, and it's important here, is that the speed of the waves water is fixed. Okay, I don't know what the speed in these water waves are, but the speed of waves in water, particular depth, is a fixed number. They travel at the same speed. So the speed of the wave is fixed, and if the speed of the wave is fixed and the wavelength has been reduced, we can therefore say what has happened to the frequency. We can say that is larger as frequency is going to equal wave speed over wavelength. So this is the equation that you may have learned as V equals F lambda, which is wave speed is frequency times wavelength. And we've just put it in the terms of frequency is wave speed over wavelength. So we just rearranged it. And if we think what happens if V, the speed, is a fixed number, and this thing on the bottom is now smaller, then frequency must be larger. So this is the sort of logical sort of pinning through there. You get 1 mark for making a comment about the wavelength being reduced. You get another mark for therefore for commenting the fact that the speed of the wave in the water is a fixed and constant value. And the third mark is for therefore interpreting that using wave speed, its frequency times the wavelength. The thing that's often forgotten in most of the explanations of this is this second point. This is the thing that people often forget, but it is critical, because if this wasn't fixed, then you couldn't be able to make any predictions at all. If you make none of these comments, but you say because of the Doppler effect, you also do get 1 mark, but you only get it if none of these are also said as well. So it's a separate point. Okay, question 5. We've got a student investigating, so we've got a 4-mark question to draw a circuit diagram to get how the current varies with the voltage across it. This is a classic question that should be an easy 4 marks. We need a power source, which is our cell. We need, we've obviously got some wires. We are going to put in an ammeter. We're going to put in our filament lamp, and we're going to put in a variable resistor, and these are all in series. And then we're going to put a voltmeter around the bulb. So what we can do is with the variable resistor, we can change the values of current and voltage that we're going to measure. Because the variable resistor, when it's got no resistance, then the bulb gets all the voltage and the current will be high. When this is at a very high resistance, then the bulb will get very little voltage and the current will be smaller. So this allows us to change things. It's not the greatest cell I've ever drawn, but it's good enough. So 4 marks. 1 mark is always for remembering the variable resistor. That is where the 4th mark is. The rest are for cell, ammeter, so correct symbols. So correct symbols is a mark. So ammeter, bulb, cell in series is your 2nd mark, and then it's voltmeter around bulb. is in your third mark. So 1 mark for correct symbols, and that doesn't have to include the variable resistor. 1 mark for the correct symbols of ammeter, cell, bulb, and voltmeter. 1 mark for them in series. 1 mark for your voltmeter, and then the final mark for having the variable resistor. Okay, then we have some data. Plot the results on the grid. It's only a 1 marker because they've done the scales and things for you. So it's plot this data, and it's quite nice and easy data because it goes along there very nicely. And then draw the curve of best fit. Okay, again, so it's drawing that. They are hard to draw freehand sometimes, curves, but you know, so 2 marks for plotting some data. The student suggests that a straight line is more appropriate than a curve because current is directly proportional to voltage for a metal. Suggest how the student could improve their investigation to find out whether a straight line or curve is more appropriate. Basically, what we want here is more data. Okay, and this could either be between values, so take it every half a volt or something like that, or we could go beyond 6 volts. So any sort of sensible comment on the fact you want more data. That's sometimes referred to as being. This is sometimes referred to as quality. Okay, this is the quality of the data. Because if you've got high quality data, you can be fairly confident, about the trends that you've got because you've taken a good range. Explain why the student should not expect current to be proportional to voltage for this filament lamp. So what we would say here generally is that it's a filament lamp, going to get hot. So the lamp gets got. No, hot is the thing I want to say. I want to say the lamp is going to get hot. That is 1 mark. The second thing that I can therefore comment on that is that resistance increases with temperature. So that's just a general sort of relevant remembering and recall about lamps. They get hot and resistance in them increases with temperature. Now, why this means we're not going to get a straight line through the origin, which is what proportional would be, that is going to be because the reason that is therefore that's going to affect the gradient of this line. Okay, so this will affect. This affects the gradient. So some comment that the resistance will affect the gradient of the line is sort of important there. 1 second, little guy. 1 second. Okay, question 6. So question 6. We've got an electric circuit. We've got a 5-mark question. So this one is fairly, it's a lot to do, possibly. We want to show that the resistance of this fixed resistor in this circuit is about 400 ohms. We want to somehow show that that is about 400 ohms, even though that looks like 460. So I'm going to correct that because that's very annoying. So we want to show this is about 400 ohms. So we've got our endpoint. So how do we get there? There's a couple of different ways. So I'm going to show you the way that I would use to get there. I know that this is a series circuit. So I know that the resistance of my thermistor plus the resistance of this, well, they should add up to the total resistance in the circuit because they're in series. Okay, so my first step is I've got the voltage that I've got, and I've got the current that I've got going through, which is 6.8 milliamps. So that is 0.0068 amps. I'm going to do that there. So my first thing actually is I can use this voltage and this current to work out the total resistance. Okay, so I'm going to first off by going V is equal to IR, and I'm going to use total voltage, total resistance. That's what I've got. So let's put these numbers in. So I've got 6.0 volts is equal to 0.0068. That's my current. Times the total resistance. I can then rearrange that. So I've got 6.0 over 0.0068. And I'm just going to get my calculator because I haven't pre-worked this one out. 6 over 0.0068. I've got 882 ohms. That's the total resistance of my circuit. And then if I think about that, well, I know that my fixed resistor is 882 minus the thermistor. So the total resistance is equal to the resistance of, and I'm just going to draw my little symbols, my fixed resistor plus the resistance of my fixed resistor. Sorry, thermistor, fixed resistor. So I have 882 is equal to 490 plus my fixed resistor. So I just do that. So 882 minus 490, and I get, so resistance of this is equal to 392 ohms, which is about 400. There are other ways to work it out. That would be the way that makes sense to me in terms of using various things. So what are we getting marks for? We're getting marks for recognizing that we're going to use V equals IR. Okay, we're going to get a mark for getting our total resistance. We get a mark for recognizing that, I guess we're going to get a mark for conversion from milliamps to amps. We get a mark for recognizing the resistances are the same, the sum of the two. And we get a mark for therefore working out the answer is 392. Okay. Then we get explain how the voltage across the fixed resistor changes when hot water is replaced with cold water. Okay, so thermostats in hot water. So we need to think, okay, what does this mean is going to happen? Well, the voltage across the fixed resistor. So if it's basically saying if I had a voltmeter here, what's going to happen is this thing gets hotter. So, well, the resistance of the thermistor is going to go down when it's hotter. So we're going to get our first mark is a comment of thermistor resistance is smaller. Oh no, so hot water and cold water. I'm going backwards. It's higher. So apologies. It's higher. Back to do the whole thing backwards. Okay, so thermistor resistance is higher when it's cold. So therefore, my total resistance in the circuit has gone up. Okay. Now, because total resistance has increased, I can then think, okay, I've got 6 volts, now I've got a higher resistance, so my current is going to go down. So current is going to go down, my current is, so whatever I'm going to measure is going to be less than 6.8 milliamps. And then we've got, so voltage will decrease as V is equal to I times R. So what we now have is this number R, the fixed resistor is staying at 400, but now I is smaller. Well, sorry, not 400, 392. Sorry, that's still 392. Make sure I'm correct there. So that's still 3. So this number is still 392, and we're now multiplying it by a smaller number. So our marks for here is a recognition of what's happening to the thermistor resistance or total resistance, then a recognition that current therefore is going to go down, and then a final recognition is the fact that voltage is going to therefore go down because of V equals IR. So we just take those 3 steps. Okay, question 7. Right. So calculate the angle of refraction for the violet light. Bit of a cheeky one. We need this number here. Okay, we know this total angle is 90, so it's 90 minus 54. You get 36. State the formula of linking refractive index. So we get a state formula. Refractive index is sine over sine r. Calculate refractive index. Plug it into the equation. So we get 1 mark for subbing in, 1 mark for an answer, and a final mark for converting it to 2 sig figs, it goes to 1.5 to 2 sig figs. So then we have a wordy question. Okay, so we've got the refraction of red light, refraction of violet light. Deduce a possible relationship between the wavelength, so lambda, and the refractive index n for colours of the visible spectrum. This is something that needs, the first thing you need to be able to be aware of is that if you think about the EM spectrum, you've got radio waves, microwaves, infrared, and then you get visible, ultraviolet, X-rays, gamma rays. Now in here, visible starts with red and ends with violet. And if you think about what's going on as we go sort of in this direction, we are going in terms of decreasing wavelength. That's the order of the EM spectrum. So red has a smaller wavelength, larger wavelength than violet. Okay, so that's our first thing. That we're going to take from our knowledge of the EM spectrum is that red red has a larger wavelength. That's our first thing. Red has a larger wavelength and it is refracting less. Okay. Okay, and that means that it has a smaller refractive index. As it enters, the bend isn't so much, so it's got a smaller refractive index. So our possible relationship is larger wavelength means smaller refractive index. Okay, that's all that means. Deduce a possible relationship. You don't need to. There's nothing that you need. There's no recall. There's nowhere that says this is the relation you need to know. But where do we get there? 1 mark is for recognizing that. 1 mark is for recognizing the diagram. We've got a small refraction, so we've got a small value then. And then another mark is for just linking the two ideas together. Right. Last question. Question 8. Okay. So. Sound waves and frequency, state the frequency range for human hearing, 20 to 20,000 hertz. That's a recall. 1 mark for getting 20, 1 mark for getting 20,000. Give the name of the piece of apparatus that you connect to an oscilloscope to detect sound waves. Microphone. So just, it's a thing you plug into for a microphone. The time period of an ultrasound wave must be measured to determine their frequency. Describe how the oscilloscope is used to measure the time period of the ultrasound waves. So there's a few things that you first need to do here. Is one is you basically need to catch, you catch it. You will have seen when people are using oscilloscopes, either the online versions or the ones in the lab, is that we need to capture a wave. So we freeze so the first thing is you can get a mark, you can freeze the wave. So there's a mark point. There are 4 marking points here, so we can freeze. So we can freeze the waves on the screen. Okay. The second thing is that you can adjust the time base to display just 1 wave. You might remember that with an oscilloscope, if you've got your grid, there's your grid. If you've got the time base and the time base setting is one extreme where the amount of time for each square is too high, then you get a signal that kind of looks like this, really close together peaks, and it's very hard to work out what's going on. So that is if your time base is too high. If, however, your time base is too low, you won't even capture a whole wave, and you might just have something that just does this, and you get and sort of it's like okay, I don't know either. None of this helps. So you want a time base setting that essentially is going to, at best, is going to trap sort of you know, basically one whole wave. Well, that's not perfect wave, so there we go. We want to trap one wave, you know, maybe two, but we don't want too many. Third mark is for saying, okay, what do we then do? So we determine the number of squares for a wave cycle. A wave cycle, and then we would multiply by the time base setting. Okay, and this there's one mark for each of these unique points. Okay, and in many ways, this is putting into words what you now have to do in this final bit. Okay, so this final question, part of the question, we've got an oscilloscope setting, we've trapped one wave. We want to say, right, okay, determine the time period of the ultrasound wave. So we want to know how many squares it is and how much is one square. It's 5 times 10 to the minus 6 seconds. So we therefore want to go, well, we've got one wave here, 1, 2, 3, 4, 5, 6. So we've got 6 squares times by this time. Okay, so I'm just checking what the calculator is going to come out to. My calculator doesn't come out in standard form, but it just comes out as being 0.00003 seconds. Okay, so that's there. Okay, or 3 times 10 to the minus 5. Either's fine. Calculate the frequency of the ultrasound waves. You can get error carried forwards. If you messed up this bit here, you can get the same for working out. We're just actually going back to the equation we used right towards the start of this paper, which is that we want to substitute our numbers into frequency is 1 divided by time period. So that equation comes up again. So we're just going to plug the number that you've got here in. So you get 1 over 0.00003. And that gives us 33,000. So basically a lot of threes, but I'm going to just do 33,000 hertz. And there we go. And that was the whole paper.